Hello again, everybody. Professor Bell with you. Looking over Lab 3, we were looking at adiabatic heating and cooling in your assignment. I wanted to at least give you some practice problems to work on to know how to set up the problems and solve for them per that lab. I did want to cover a couple things here real quick, though, about the motion of air and what really we're talking about with adiabatic warming. So if you look at, say, uh, this first slide is showing you, of course, rain over the equatorial regions, over a rainforest such as the Amazon, the Congo, or the Malay Archipelago. But basically, it's hot there all year. That because it's warm, warm air rises. As that air rises, it expands and cools off. And as that happens, then you see rain come out of it. And um, the rain is the intertropical convergence zone in the summertime is going to be in the northern hemisphere where it's going to be the wet season. In the southern hemisphere, during the northern hemisphere summer, that's going to be the dry season, and it flip flops back and forth. So anyway, point being is this is how you get rain in the equatorial regions. Orographic, the oro is referring to a mountain. So in this particular situation, they're showing you this band of mountains right here, and that air is being forced across it, coming from the ocean and then forced upward. And again, cooling at a rate that is different than the environmental lapse rate, which we're going to look at in this lab. But point being is that it is forced up again as it moves higher in altitude. You have less air pressure, and with less air pressure, expansion, cooling, the air mass, the volume of air does not have the ability then to hold all the water vapor it has, and eventually you'll get rain on the windward side of the mountain. Over here on the leeward side, you'll see that there's rain shadow and very little rainfall. Okay, and then finally here with frontal activity, it's trying to show you here essentially a cold front moving into invading an area of a warm front. The warm air is pushed aloft, cools, condenses, rain. Okay, and there's convergence as well used in your textbook. So those are the four mechanisms. Convergence being that the air is colliding in a particular area and has nowhere to go but up. It's certainly not going to go on the ground, so that's what you get. Okay, looking at orographic rainfall patterns. Again, this air mass is pushing in, blowing in from the ocean to the land, and then it faces a barrier here. This mountain range, at some point, if we're going to look at it, your examples have an event where no rain occurs and then another event where some rain occurs. So in this particular example, it's showing you precipitation on the windward side of the mountain, and that maybe it kept raining and or snowing all the way to the peak. And one thing I want to point out to you is this: just because the air mass gets to the peak of the mountain doesn't mean it immediately stops raining at that point. In fact, that air mass is going to travel out and overshoot that mountain a little bit, and it's going to drop rainfall and snow on this side. This is why you'll actually see snow on both sides of the mountains, but you'll see it start to peter out as you go further and further onto the other side. And why? Well, it cooled adiabatically, so it's going to warm adiabatically. But where you don't see rain, that's the dry adiabatic lapse rate. Where you see rain, ta-da, wet rate. Okay, and it's those different cooling and warming properties that lead then to leeward side rain shadow effect and desert conditions. And that's why I gave you this example with a physical mountain that you had to deal with. Let's look at it in satellite imagery though. Okay, so this is India right here. These rivers right here, this is the Punjab region of India. Punjab means 5 rivers, and this is the Indus. You've also got the Ganges and Yamuna rivers. But why is it so green right through here in this satellite image? Well, it's called orographic precipitation. And so, especially during the rainy season, the monsoon season here, all of this is just getting torrential rainfall. Well, the higher elevations you get, what? It's colder, falls as snow, becomes glaciers. And then when it peaks over this area, what ends up happening is all the moisture, or at least most of it, has been wrung out of it, and it's just not going to have any more snowfall. Why is it so brown in here? Say like the Taklamakan Desert. That literally means, if you translate it, the enter but never leave desert. So you get people living around the edge of the basin itself. Okay, the Tarim Basin here, so they can hang out around those areas where glacial melt It comes down, but you're not going to farm in the middle of this thing any more than you're going to do wide scale farming up here on the Tibetan Plateau. All of this is the Tibetan Plateau. This is the Qinghai Plateau in China as well. And so they'll have maybe little gardens that they can tend on the small scale, and certainly cold vegetables and things of this nature, but they're going to have uh, goats and sheep and yaks and all kinds of animal husbandry is what they're going to do up here. So a lot of dealing with meat products and milk, things of that nature. But again, showing you where is the rain and then the rain shadow. Okay, and this one is from Washington State. So you've got the Columbia River Basin here, Puget Sound and all this, but most of the air, because it's in the westerlies wind belt, is blowing from the Pacific Ocean and in this direction toward the east. Okay, so it does encounter some of these coastal ranges, and depending on the conditions, you may actually get snowfall in some of these areas, but these aren't really dominant mountains. It's these cascades that are. Okay, so you see more rainfall and snowpack, which is good in the summertime because as this melts, it feeds these cities out here in the western part of the state. The interior part of the state, not so much. So again, rain shadow effect. However, if you dam this river up, and they've dammed the Columbia and Snake and all this area, just like we have in the Tennessee Valley. So think TVA, hydroelectric power, and everything associated with that. There's a lot of agriculture that goes on here based on the usage of those rivers. All of that's to say, now you've seen it in graphic and satellite imagery. Let's go ahead and address your problems that you're facing here. So you've got two different lapse rates that you're dealing with in this first graphic, and I'm telling you now, I'm not doing the second graphic. I got to leave some of this to you guys to figure out on your own, but I'll walk you through this with new examples to show you how you calculate. Okay, so if we're looking at the environmental lapse rate, what we're looking at is stratified air. So even though the 65 is here and shows you it's that's the temperature of the moving air mass, we're using that as the base for our stratified air as well. So that's the constant. Okay, notice the elevations here. So I've changed these elevations from the ones that you're using in your problems to be 500 feet above mean sea level, 1,500 feet, and 4,000 feet above sea level, and then back to 500 again. So if we're using stratified air, we're doing the 3.6 degrees Fahrenheit per 1,000 feet. So what this really literally says is if I'm standing on a spot on Earth and all things being normal and equal, if I were to go 1,000 feet directly above my head and take a measurement, it should be 3.6 degrees different. Now, this is a number one problem I see whenever anybody does this is they tend to add everything. But if we're going up away from the earth, you're subtracting. It's getting colder as you're going upward. So remember that in the end, these values at 1, 2, 3, 4, these, since we're going up, they should be less than this. We're not dealing with any temperature inversions where it actually gets warmer as we rise. That's not what's happening. So always make sure that your numbers, at least here, are in descending order. And then of course, if we go back down again, it seems like what should we do? We should add. Okay. So let's do this one right here first. Clearly we see we need two different sets of data. So this one right here is 1,000 feet different. So I'm going to show you the answer right here. So this is actually the answer. Okay, but here's the problem that you set it up. So you take the 1,500 feet, subtract the 500, gives you 1,000 feet. Now think about that as just one, because that's what our equation says here. For every 1,000 feet, you subtract 3.6 degrees Fahrenheit per that 1,000 feet. So you could do that math in your head. And I'm trying to show you that that's how I do it too. There's a way to set these problems up as fractions and canceling out numerators and denominators. I'm not a mathematician and I'm not doing it that way. If you know how to do it the way you were taught in math, good for you. But I was terrible at math. But I'm actually putting this in here because I seriously had math phobia. So I don't want you to have math phobia. Anyway, so this is what? 1 times 3.6 or 3.6 degrees Fahrenheit. So I take my base temperature and what do? Subtract the 3.6 from it, and that should give me the 61.4 degrees Fahrenheit. Pause the video now and see if you can figure out the number 2 problem, okay? And of course, it does mean you subtract 500 from 4,000 and go through it, but pause it, and then I'm going to go ahead and now show the answer. Okay, so the way this works is, again, we take the 3,500 feet, 3.5 times 3.6 should be 12.6. Okay, so I took my 65 here, subtracted the 12.6, and got a value that I didn't change. I did a copy and paste here. Crap. Double check me. Obviously, that one's going to be wrong, and I should correct it, but I'm in the middle of it, so I believe it. But double check that number. That number 52.4 should be that value right there. Okay, so sorry about that, but double check. All right, check this one out now. Now we're going to use the moving air, the rising air mass. So we're using the dry adiabatic lapse rate. So we don't ever see precipitation begin. Okay, so since that, we're not going to use the wet adiabatic lapse rate. We're only using the dry here. So take again those differentials. Let's pause it if you want to, and then work the problem, and then I'll show you what I got. So here's how it works. The 1,500 minus 500 gives you 1,000. 1 times 5.6, because that's our rate, should give us 5.6. 65 degrees minus 5.6 should be 59.4. Okay. And then just do the same thing again with instead of, and by the way, I don't care if you use 4,000 minus 500 or 4,000 minus 1,500. As long as you got it right, you can work from that. Just remember not to conflate or interchange those. If you're measuring from this elevation, then use that value. If you're measuring from a 500-foot elevation, then use that one. Okay, but I'll go ahead and show you these answers and wrap up this video, but pause it and then you work on it and see if you got what I got. But as we see here on this next one, I've got 45.4 degrees Fahrenheit. If my math was done correctly, please check it. Remember, I was doing copy and paste and I just forgot to change that value there, but that one matches up. And then the simple thing to do is not do anything on this one and just take your 65 and plug it in over here. That works, but it's also dangerous. I want you to know why it's that way and do it together, because once you add in a varying lapse rate like the wet adiabatic rate, again, I'm not going to show you it. That's for you to figure out, but these values will definitely change, and you can't just up and superimpose one value for the next. It's that's it. So I hope this has given you just enough to be creative and dangerous and move forward with Lab 3. All right, talk to you again. See you later. Bye.